Alright, here we are back again. We're going to shed some light on some subjects today, primarily that about light. We've talked about electricity and magnetism, as well as sound waves and so forth. And now we're going to talk about light waves. And light waves are a type of electromagnetic wave. And electromagnetic waves, not surprisingly, involve electricity and magnetism. Basically, if you have an electronically charged object and you move it, then it's going to send out electronic waves. Just like if you take a stick and wave it in the water, it's going to send out little ripples or waves in all directions. So if something with an electronic charge starts to move, it sends out an electric wave, and that's represented by the up and down vertical axis, if you will. All right, but we know from our electricity and magnetism that if you have a changing electric field, which you do as this electric charge wave goes through, it's also going to create a changing magnetic field. And you see this other field going back and forth on a horizontal plane. All right, and that would be the magnetic field. As the electric field changes, the magnetic field changes. The magnetic field changes, the electric field changes. And so it's kind of a constant trade-off back and forth. As this one changes, it changes the other one, and they're constantly going perpendicular to each other. Okay, and they're traveling in this direction. Okay, so if I go from here to here, one of them going back and forth horizontally, one of them going up and down vertically, and as they change, each one of them changes the other. And so you have an electromagnetic wave. Okay. Now, the quicker the object is vibrating, then you would have a higher frequency of the wave. If you remember waves, that would be a one wavelength. How many wavelengths go by per second would be the frequency. Or if it's how many go by per second, we usually call it hertz, the number of hertz in that electromagnetic wave. All right. Now, electromagnetic waves come in a variety of sizes, and we are familiar probably with a lot of the names of those, and have probably studied them in school before. This is an example of at least a partial list. All right. We start off with the long wavelengths, which means that they have a low frequency. So the lowest frequency electromagnetic waves are radio waves, and the distance between the length of one wavelength may be a football field or more. So these are very long waves, especially as you get back toward the very beginning here. Radio waves, we have fairly low frequency radio waves. Then we work our way up, and we have TV waves. There's UHF and VHF. VHF stands for very high frequency, and you used to have two knobs on your TV. One was for about the first 13 channels, and then you put it on a UHF, which is ultra high frequencies, even higher frequencies of radio waves. Okay, and they were used to do channels above that. Okay, and so originally you just had like usually 3 local channels, the main networks, but then as you got more and more networks, and you had to have these other channels, and they're in the little higher ones. Beyond that, though, are microwaves, which we use for cell phone reception. Obviously, we use them to cook things. Also, different types of microwaves. As we go over here and they get higher frequency, we overlap into infrared, which is primarily heat. We think of that in terms of heat. And then we have visible light. These are the light frequencies that we can actually see. Notice it's a very small part of the electromagnetic spectrum. I believe if we could stretch this out into 1,000,000 feet, only 1 foot of it, or 1/1,000,000th of the whole spectrum, would be visible light. Okay, it's a very small piece of it, but it's very important to us because that's what we see with. All right. Ultraviolet reaches on to the next category, followed by X-rays, and eventually, finally, the highest frequency, highest energy, gamma waves. So basically, we see the thing here, the low frequency going to high frequency. We have low energy going to high energy. X-rays, gamma rays are very high energy levels, and to the point that they can become dangerous and cause mutations in cells, cancers, things like that. Exposure to them can cause a lot of damage to our body cells, causing a lot of problems. Or they can turn you into big, mean, and green like the Incredible Hulk. But the odds are much higher that you're going to be, I wouldn't bet on it. I would go with the extreme damage to your body cells. All right. So as they go higher and higher, you can see that they become more high energy, and so low energy to high energy, low frequency to high frequency, long wavelength to shorter wavelength. The shorter the wavelength, the higher the frequency, the higher the energy. All right. Now, how are these waves different? How are radio waves different than microwaves? Basically, they're not. They're all the same type of waves that we talked about here with the electromagnetic. There's an electric charge that is vibrating. It's sending out these pattern of waves. The only difference is their frequency. So very likely you could say infrared is just a low frequency of visible light, or a infrared could be a high frequency radio wave. They're the same type of energy, same type of thing. They're caused by the vibrating electrical charge. It's just a matter of the frequency that they vibrate at, and that gives them different properties. We can only see this little short visible light here. Some animals can see infrared, some can see ultraviolet. We do not. Okay, we only see that little section that we do. So really, it's not so much that these are different kind of waves as much as they're just different frequencies, and at different frequencies they have different characteristics and different effects for us. Okay, the names, it's not like there's some definition of radio waves that makes them different than microwaves, other than the fact that they have a lower frequency, longer wavelength. Okay, that's it. Okay, now we can use them for different things, but there is no actual difference in the actual wave. All right. Now, one of the things that we talk about with different light and so forth is we use words like transparency, and we use words like opaque. And the good question is, what exactly do those words mean? All right. And basically, opaque means that it will not allow the wave to go through the material and be re-emitted on the other side as the same type of energy. Okay? Now, for example, if someone asks you, is glass opaque or is it transparent? Well, normally we say transparent because it is transparent to visible light. Visible light, what we can see, when it comes through and it hits glass, it is absorbed by the atoms in the glass and passed from atom to atom, but it comes out the other side and it is re-emitted still as visible light. And so it slows down a little bit as it's being passed from atom to atom in the middle here, but basically it still comes out on the other side and it still comes out as light, and therefore it's visible light. And say that glass is transparent because it comes out the other side the same thing. Now it slows down in here. This shows atoms as if they were gulping and burping and passing the energy, but basically the energy hits the electrons, it could pass to the next electron, and if it gets spit out eventually on the other side as the same type of energy, then we say it's transparent. Ultraviolet light, on the other hand, comes and hits the glass. When it hits the glass, it makes them vibrate so much and for so long, although it's only 100 millionths of a second, but compared to visible light, that basically they vibrate and turn it to heat, but they don't pass the ultraviolet light through the other side. Therefore, we would say that glass is opaque to ultraviolet light. All right. Now, infrared, on the other hand, infrared light comes and it basically heats up molecules of glass, whole molecules, and they vibrate and it raises their temperature, but they also do not get passed through. So the heat or infrared does not pass through. Now, since it does heat up the glass, sometimes we call this infrared is heat. Someone says, well, how does the greenhouse keep heat in? That's all the whole point was to let light in and it gets fairly warm. But the fact is, the visible light, once it hits the opaque objects, which may be the flower pot, the floor, anything else inside that's opaque, once again, it absorbs the energy from the light, but it does not re-emit it as light. Usually it re-emits it as infrared. Well, when it gives off infrared, as it travels back to the glass, it can't get out. And so eventually, as more and more light comes in and it's released as infrared, that begins to build up heat inside the house. And so we have a hot house or a greenhouse. And so it actually begins to get a little hotter and hotter. And then at night, of course, you have no new light coming in, and the heat gradually passes through the glass into the cooler night air. And so the next day, though, when the sun comes out, once again, visible light comes in, infrared is released, but it can't get out, so the greenhouse will heat up again the next day. Metals, when light hits them, they vibrate, but they tend to They have a lot of free electrons and they vibrate, but they don't pass it from one atom to the next because, if you remember, their electrons just kind of float around on their own. And so most of the energy is just reflected back off, and therefore light energy and things like that are reflected, and therefore metals appear to be shiny. Why? Because they're just reflecting the light rather than let them going through. The atmosphere is opaque to high frequency, ultraviolet. Okay, so in the higher frequencies, and that's a good thing because that would be highly damaging to us if they allowed it through. Some of the lower frequency UV, however, is able to get through, and this is the ultraviolet light that can cause sunburn, and repeated exposure over time can cause you to have skin cancer. Okay, but it does block a lot. It is opaque to a lot of the higher frequencies, which would be much more damaging to our skin. It does allow it's transparent to visible light, obviously, and the atmosphere lets that through, and it lets some of the infrared heat also come through. Now, clouds are semi-transparent, which means they'll let some of UV through, but not all of it, of that lower frequency UV. And so you can get sunburned even if it's cloudy outside, particularly if you're on the water where it gets reflected back up. So it hits the water, reflects back up into you, or metal around the shiny metal surfaces. I guess the same thing could happen. But basically, since they let some of the UV light, some people think, oh, it's cloudy outside, I can't get sunburned. But yes, you can, and that's primarily because the clouds are semi-transparent to UV light and let some through of that. The thing about electromagnetic waves, before we go into the next section, is this, how fast they travel. Frequency is just how many wavelengths there are in a certain length of time. It does not tell you how fast. All electromagnetic waves move at the same speed, which is roughly equal, or is exactly equal, to the speed of light. And the speed of light, which is represented by the letter C, is 3.0 times 10 to the fifth kilometers per second. A kilometer is half a mile, so about half a mile. So they're going about 300,000 kilometers per second in a vacuum. If there's no air or anything like that, it'd be slightly lower in air, but basically it's the same speed. Okay. Now, as it goes through different materials, all right, then it can be different amounts. And while air is practically the same, it will slow down in these different amounts. So, for example, in water, all right, if an electromagnetic wave goes through water, or light goes through water, it would end up being about 0.75 C, or about 3/4 of the speed of light. It would slow down a little bit. Glass, all right, would slow it down to about 0.67 C. Okay, so closer to half, about 2/3 of that. And finally, if it were to go through a diamond, all right, it actually slows it down by less than half, by more than half. It's actually 0.41 Cs. Okay, so the speed of light. So it would slow it down. Water about 3/4, glass by about 2/3. It only go about 2/3 the speed, and diamond would slow it down to less than half. Now, this difference in speed is very important. Okay, and once it goes through the water or the glass or the diamond, it would once again pick up at the regular speed of light and come out the other side once again at 3.0 times 10 to the fifth kilometers per second in a vacuum. But this will be later when we talk about light and using lenses and so forth to bend light. It has to do with this difference in speed as it slows down through these things. All right, and so we'll be talking about more of that when we get there. Right, we're going to introduce one more concept before we leave for this video and go for another one. But the idea of reflection. The idea of reflection is that you have light that is coming in, it hits the mirror, and it bounces off. Okay, and so the law of reflection states that when it bounces in, whatever angle it comes in, it is going to bounce off at the same angle. All right, and that is just the law of reflection, and it has to do that. That's just the way light behaves. And there's a line perpendicular to the surface it's bouncing off of. We call that the normal. All right, and so the incident ray is the one that's incoming, and the angle of incidence between the normal, that perpendicular line, and the incoming ray, that's the angle of incidence, and bouncing off is the reflected ray, and the angle between it and the normal is the angle of reflection. And the law of reflection states that the angle of incidence is always equal to the angle of reflection, and that's a rule that light always follows when it reflects off of things. Alright, talk more about that and other things with the reflection and so forth in the next video.